Okay, we got a three-phase synchronous motor here. We're going to hook this up and put some load on it, and we're going to see what happens with varying loads. I'm not going to use a tack because it's a synchronous motor. The speed will, once we get that that link established, the speed in this motor will stay at 1800 RPM. But what we're wanting to see here is how we change our field current and what that's going to do to our line current and what that means. So I'll get this up and running. See our line current's hitting about 9.6 amps. There's no load on this thing. I'm going to energize our field, and it just pulled into synchronization. Current dropped down from 9 amps to 1.3. Okay, so now this motor is running at 1800 RPM. Okay, so this motor's up, it's running. If we reduce our field current, we'll come down to 1/4 amp. You see our current came up quite a bit. Okay, with the field underexcited, so less field than the magnetic field than is required, this motor's running at a lagging power factor. So we've got a current of 6.8 amps. Now as we increase the current, we go from 6.8, go up 1/4 to 1/2 amp, goes down to 4.8. Uh, 0.75 amps, 3.2 amps of current. Increase that a little bit more. So at an amp of field current, we've got 1.6 amps of line current. One and 1/4 amps, 1.3. Amp and a half. Our current's starting to come back up. We got 3 amps of current now. One and 3/4 amps. We're up to 4.3 amps. And we'll take this up to 2 amps, and we've got 6.4 amps of line current. I'm going to put some load on this alternator now. So I've got 12 amps or 12 Newton meters of load on this machine. At 2 amps of field current, we got 9.9 amps of line current. And as we bring our current down, so at 1.75, 9.2, 1.5, we're down to 8.8. 1.25. That back at 9. 1 amp, back up to 9.9. 0.75 amps of current, we're up to 11.5 amps. Oh, and now you'll see our fields are jumping all over the place. So when I went down to 0.5 amps of line current, what happened there is there wasn't enough magnetic field being produced on that rotor to maintain that magnetic link. So that motor actually dropped out of synchronization, and our currents went up, and it bounced around. It was doing terrible things. So we needed at least half an amp of. We needed more than half an amp to maintain our field current. You see these? Yeah, I recorded these, our numbers on the board here. So with no load, as we started out at 1/4 of an amp, went up to 2.0. You can see our current started out high, dropped down. This was our lowest point, and then it started to come back up. So with no load, this motor had a power factor of 1, or it was at unity, with 1 1/4 amps of field current. That means that everything before here was lagging, and here we were leading. A little low on the board. Wow, I rate terribly. Okay, the further we get away from that unity power factor, the more leading or the more lagging it gets. Once we loaded that machine up, we started here and we're dropping down the current. You can see that we were slightly leading here, 9.9 amps, came down to 8.8. So that was 2, 1.75. So now our power factor equaled 1 at, put some grids in here so we can keep these numbers straight. So when it was loaded up, our power factor was 1 with 1.5 amps of field current. So because there was that extra load, in order to keep that torque angle, or to hold the torque angle, to hold the magnetic link, we needed an extra 1/4 amp of field current. So that's why our power factor is now happened at 1.5 amps of field current rather than 1 1/4. And then of course as we go this way, we become still more lagging, and on this side is leading. When you graph those out, our power factor will, your power factor will start out at a low value, at a low value, it'll rise to 1 and come back down, right? So your power factor curve will look like this, right? Started out as a decimal, comes up to 1, then returns as a decimal. Anything on this side is leading, anything on this side is lagging. Your line current will be a V, right? So this is your power factor, line current, or field current. Line current on the reference will have our line current's going to come down and go back up, and this is in relation to, line current is on this side, and that's as we take our field current. As our field current gets bigger, our line current starts high, drops down to a low, comes back up. Power factors in the opposite graphical representation of your line current. Sorry, I stumbled there a little bit, but that is the what goes on with a synchronous motor. So when we started it, had a high line current of 9.9 amps. As soon as we got that magnetic link established with no load, our current dropped down to 6.8, and then as we increased our field current, it was still lagging there. We got it to unity, and then started to give it a leading power factor, and we loaded it up. And as we started, it was still leading even with that with the load on it. We dropped down. We hit unity roughly 1.5 amps, and then it started lagging. So you can see there was a slight difference in where it hit unity, and that's based on the torque angle of that machine. Okay.